Okay, we're going to talk about exponential growth models and linear growth, and we're going to compare them. So these are two very common models that you'll see in science and in everyday life. We use these models quite a bit. Linear models are extremely valuable because, well, for one thing, because they're relatively simple, and there are a lot of things that we can use, and they can be approximated with a linear function very well. Exponential growth is extremely important. It happens often in science and in many other situations in finance. So we're going to talk about finance right now. We're going to talk about salaries. Quite often when you get a raise not a dollar rate. Sometimes you get that as well, depending on if you're an hourly worker or salary worker. But quite often you get a raise based on a percentage. So we're going to compare two different models, two different scenarios. So somebody gets a starting salary. The starting salary is at $40,000, and one possibility is to get a 4% raise per year. It's in the contract. When they sign up, say, okay, every year you're going to get a raise, and it's going to be 4%. Another one, you say, okay, you're going to get a raise every year, $1,700 per year. And so we're going to take a look at these. If the question is which one is better, then just like in many different questions, the answer is, well, it depends. So it's not necessarily a yes or no question. It depends on many different variables. It might depend on a personal preference sometimes, or it might depend on other factors like how long you plan on having the job, things of that nature. What are your immediate needs? Okay, so now there are a few things that we need to know. One of them is the initial value. The initial value is something that's the same in both of them. The initial value, it just means, the beginning value. How much did he start off with? So when worker A starts off, how much is he making his first year? Well, his first year, he's making $40,000. Okay. What's the initial value for worker B? Well, the first year, okay, when he first gets the job, right? He shows up, he hasn't been working any years at all. That's why it's 0. So that's the initial, where the initial value is. When X equals 0, Y is your initial value. So what is the initial value in this case? Not $1,700. I wrote the wrong thing down. $40,000. That's how much he's making when he first starts the job. Okay. After 1 year, they both get a raise. After 1 year, worker B, he gets a $1,700 raise, $1,700. So that means after 1 year, he's making $41,700. Okay. So anyway, the initial value is exactly the same for both of them, but we use different letters. So for this model right here, where we have percentage, this is going to be our exponential model. And this one right here is going to be our linear model. So for exponential model, we're going to use the initial value, we're going to use to be equal to A. So we're going to write that down. It's just 40,000. The initial value for a linear model, we're going to use B. Now you may know this as the y-intercept. Okay, so the y-intercept of a linear function, we write that as B. This one, by the way, would be the y-intercept as well. So this is also your y-intercept. Okay, so our y-intercept would be 0, 40,000. Here, same thing, 0, 40,000. Okay, so that's our y-intercept. Sometimes keeping track of these letters can be a little confusing. Like I said, B in the linear model means something completely different than B in the exponential model. B in the linear model is our initial value. It's our starting point. A is our initial value in the exponential model. Now, the way they grow is what's different. Okay. So in the linear model, we get repeated addition. So what we're doing is after 1 year, we add 1,700. After the second year, we add another 1,700. So we add 1,700, we add 1,700, we add 1,700. So repeated addition, what that leads to is multiplication. Repeated, over here, we're going to do repeated multiplication. Oops, I spelled it wrong. Okay, so repeated multiplication is what we're going to be using here. So repeated addition, like here we do 1,700 plus 1,700 plus 1,700. So we would add one, add another one, add another one. That would be for the third year, right? That would be the same as 3, 1, 2, 3 times 1,700. So this would be 40,000 plus 3 times 1,700. So that's what the value will be. So you could calculate that with a calculator just by multiplying that, or you could add it one at a time. For the exponential model, we're going to be doing repeated multiplication. So remember, now this one, our B value, okay, that's what is going to be our growth factor. So notice it's the same letter, but you have to be very careful. They mean completely different things depending on what we're talking about. If it's exponential, B is the growth factor. If it's linear, that's our starting value. Okay, so B is our growth factor, and it's going to be 1 plus the percentage as a decimal. So 4%, remember we move that decimal place 2 places, 1, 2, so it's going to be 0.04. So that means we add 1 plus 0.04 to give us 1.04. And that's going to be our B value. So this is the value we're going to multiply 40,000 by. So 40,000 times 1.04 is going to be what you get for the first year, which is 41,600. Now, if you notice, if you compare these two numbers, 41,700, 41,600, for the first year, it's better to go with the linear model, right? You don't make quite as much money exponential right there. Now, the second year, we're going to take the 40,000. Now, this is what we had before, and then we're going to multiply it again. So just like over here, we kept adding 1700s. Here we're adding, and we're multiplying by another one of these. So we keep doing that. All the way down. And remember, that's just a shortcut. We can use a shortcut for repeated multiplication, and that's our exponent. So that's 3. For 4, we would have 40,000 times 1.04, and instead of writing 4 of these out, we just write that. Okay, and we can calculate this just like this, and just like that over here, we can do the same thing on this one. We can write it as a shortcut. So we start with our 40,000, and then we have to add 1,700 for each year, right? And there's 5 years. So it's 5 times 1,700. So whatever that turns out to be. So this one right here, $40,000 times 1. Let's see, what do we have? So what do you get? You get 48,666. Okay, now for 5 on this one right here, 5 years, after 5 years, you're making 40,000. So that's the beginning part. Then your raises are going to be 5 years, and each year 1,700. So for 5 years, it'll be 48,500. So by the time the 5th year comes around, the exponential model is a little bit more than linear. But is it really enough to make a difference at this point? It's hard to say. You have to make that decision if it's your job and you're getting it. Because remember, you're making more money here for this one. So you make more money earlier, even the second year, the third year. So after 4 years of this one, okay, let's see, I made a mistake, didn't I? I definitely made a mistake. So 4 years plus 4 times, okay, 46,800. Okay, what about 4 years on the exponential model? Oops. Okay, 46,794. Okay, so they're almost the same, but this one's still a little bit more. So it's not until the 5th year that this model actually starts to lose out. So all that time you're making a little bit more money this way, so you have to decide, well, is that better or is this better? Okay, so if you're only going to keep the job for 5 years, you might want to go this way. But then once you start to go more, look what happens when we go 10 years. So we do 10 years. Now we're talking about 40,000 times 1.04 to the 10th power. And what do we have? 59,209. For 10 years on this one, we have 40,000 plus 10 times 1,700, and we end up with 57,000. Still not too much difference, but $2,000 a year, $2,000 is a lot of money, right? I mean, so it's not so close as it was before. Now it's starting to look like this is maybe the better deal if you're going to be there a long time. So there's a lot to go into it. Make sure you understand that, that the better model, the better choice on something like this, on an investment or on a job choice, depends on a lot of different things. Now, as far as the equation, okay, so if you need to write the equation for this, you want to look at the pattern. Ask yourself what's happening. Okay, so first of all, everything in this column is a y value. So what's the y value equal to? Well, if we have x equal 10, then this is what we end up with. 40,000, 1.04 to the 10th power. If x is equal to x, then it's going to be 40,000, 1.04 to the x. That's our equation. So whatever, you want to look at what's changing in the equation and how it's changing. So every single line we have 40,000. So we're going to keep that 40,000. Every single line we have 1.04. The only thing that's changing is the value of the exponent. And that exponent every single time is exactly the same number as the x. So we can just use it that way. Over here, every single line has a 40,000. And every single line has 1,700. The only difference is and they're adding. We're adding here. The only difference is what we multiply this by. So at 5, we multiplied by 5. If it's down here at x, we would multiply it by x. So that's our equation. And normally you would write the 1700 in front, like that. But the order you write these in doesn't matter. We have, this is exactly the same as that. This is just the standard form in slope-intercept form. Okay? I know that's a